So in this entire unit, we are going to be looking at rotating systems. And here I have a cylinder it's got a string wound around it. And the string is hooked up to a weight or a mass that's going over a pulley clamp. So that when I let it go, here we'll watch it. Oh, I changed the speed to 1/8. Let me speed it I'll go up to normal speed. There we go. Now we'll go in slow motion. Okay, so what's happening here is there's acceleration, right? The cylinder on the left is accelerating, but it's accelerating in a circular way. And that's what we're going to be studying. So that's why it's really important that we understand circles to begin with. So things like arc length, angle, and radius. Okay, so let's go to notability here. So I put this into video physics, and in video physics, I saw that the weight that's hanging over the pulley clamp actually accelerates. And I can see that in my position versus time and my velocity versus time graph. It's certainly not perfect, but it's pretty darn good. Remember, if my velocity versus time graph is a straight line, the slope of this is going to be acceleration. And what I'm going to try to do in this unit, or what we're going to do, is we're going to relate the acceleration of this mass over here to the acceleration of this rotating canister. That's what we need to do. So I'll come back to that in a bit, but I just kind of wanted to get you set up with the thinking. So we're going to use a lot of ideas that we used previously, ideas from kinematics, but we're going to apply them to rotating systems. So here I've got a picture of a circle. I've got the center of the circle, and I've got a point on the circle, and I want you to imagine that the point is rotating. Again, in my picture here, I'll play it one more time, or back it up here. I have a point, it's a thumbtack, and you can see that thumbtack rotating. So that's what we're trying to imagine here. So I've got a point rotating around the circle, and delta x is the distance, the portion of the circumference that it covers. That delta x is also known as arc length, and in a math class you might see it called x. For us, we're going to give it, sometimes you'll see it called linear speed, sometimes you'll see it called tangential speed, because at any given instant the speed is tangent to the circle. But the speed of that point would be delta x over delta t. We know that from before. Okay, so what we're interested in looking at is the relationship between this arc length and this angle, because we've also got this angle being swept out over time. In fact, if I were to have 2 points on the circle, both rotating but with different radii, they would have the same, what we call angular velocity. So angular velocity is the change in this central angle over the change in time. The symbol for angular velocity, this little squiggly W, is a Greek lowercase omega. But we'll just say omega. And again, omega stands for angular velocity, and it's measured in radians per second. Okay, so I made a video talking about radians, but I'll put the definition here. A radian is a unit of angle measure where one radius, so what we did in the last video is one radius was laid across the circumference of the circle and sweeps out Actually, let me start over here. So we would take one radius, pick it up, and lay it over this portion of the circumference, and the angle that is swept out is 1 radian. And we know that for half a circle is pi radians. The whole circle would be 2 pi radians. And that also equals 180 degrees. So if you want some kind of conversion factor, pi radians equals 180 degrees for a circle. Okay, so the angular velocity can be computed if the time for one revolution is known. So delta theta equals 2 pi for 1 revolution. So delta theta over delta t, or 2 pi over delta t, would give us the angular speed. So if I go back to this example, if I wanted to compute the average angular speed of this object, I start at 0 seconds. Oopsie. Let me go back here. There we go. Start at 0 seconds, and let's see how long it takes for it to go around once. Took about 0.57 seconds. So once around was 2 pi radians over 0.57 seconds, and then I could convert that to a decimal to get the value. I'll do it. 2 times pi divided by 0.57 is 11.02. Now this is an average velocity because we actually know this thing is speeding up. So we'll talk more about the acceleration in an upcoming video. But for now, I just want you to be able to picture it. Okay. Now what's cool about this is, what if I wanted to find the angular, not the angular speed. What if I wanted to find the linear speed? How far did the thumbtack go? How far did the thumbtack go? So in order to figure that out, I need the radius. So I did get out a ruler and measure the radius. It's pretty cool, actually. This canister is from a product from Germany, and it's had a diameter of exactly 10 centimeters. So the radius is 0.05 meters. And so I could figure out the circumference of this thing would be 2 pi r. That would be 2 pi times 0.05, which would be 2 times 3.14159 times 0.05, which is 0.314. And if I wanted to find the speed of that thumbtack, I would take the circumference over the time for 1 revolution. So that would be 0.314 meters to go around once, and then it was 0.57 seconds. And that's 0.55 meters per second. But here's the deal. To calculate this, I took 2 pi r over t. I had already figured out the angular speed by taking 2 pi over t. The only difference between these two things, oh, that didn't look so nice, did it? The only difference is that r. So if I took the angular speed and multiplied by r, I would get the linear speed. So that's our next formula. Oops. I didn't want to save that there. Okay, so when you look at the formula for angular velocity, and it's just 2 pi over time, the formula for linear speed is very similar. The only difference, look, is that r, 2 pi r over time. So angular speed is 2 pi over time, linear speed is 2 pi r over time. And the relationship between these two numbers is if I would take angular speed and multiply it by r, I would get linear speed. And that's what this formula is saying. Okay, so I'm going to do, let's do example 2. Before compact discs, music was played on vinyl records. The records rotated at 33.3 RPM or 45 RPM. Convert 33 RPM, rotations per minute, to angular speed. Okay, so 33 rotations in 1 minute. I like to draw a chart like this. I guess there's a lot of different ways to do this, but what I'm trying to do is get things to cancel. So 1 minute has 60 seconds in it. I want the minutes to cancel, so I put minutes on top when I put my conversion factor in there. Okay, now a rotation, one rotation is 2 pi radians. So if I do that, rotations will cancel. And this is looking good because what I want left is radians per second. That is what angular speed is. It's radians per second. Okay, so I'm going to multiply what's on top and divide by what's on the bottom. So I've got 33 times 2 pi, that's 66 pi over 60 seconds. You could reduce this by dividing by 6. You could get 11 pi over 10, and you could leave it like that. You could say 11 pi over 10 radians per second. Or if you don't dig it, you can use your calculator, and we would get 3.45 radians per second as a decimal. Okay, let's practice another one. 45 RPM to angular speed. Okay, so this is rotations, per minute. So I'm going to do the same thing. I'll use slightly different notation just in case you've seen it a different way. So again, 1 minute is equivalent to 60 seconds. And 1 rotation is equal to 2 pi radians. So again, I'm going to multiply everything on the top and divide by everything that's on the bottom. So this would be 90 pi over 60, which reduces to 3 pi over 2. Or again, if you'd like to change it to a decimal, we get 4.71 radians per second. Okay, part C. If a record has a diameter of 7 inches, find the linear speed of a point on the edge of a 45 RPM record. Okay, so this one will give me a chance to explain what I'm talking about. So, let's see. I'm trying to get my record to be concentric here, but I'm not doing so hot. All right, well, it'll have to be good enough here. So the record does have a diameter of 7 inches. These are kind of back in now to make a 7-inch record. So the radius is 3.5 inches. Oopsie. And what I know, well, let's convert that. So 3.5 inches to centimeters. So I'm going to do 2.54 centimeters per 1 inch. Inches will cancel. So I get 8.89 centimeters. That's my radius. So I have the angular speed, omega, up here, 4.71 radians per second. So the beautiful thing is that angular speed times the radius is the linear speed. So 4.71 radians per second times 8.89 centimeters per, here's the cool part, a radius is a distance per radian. There's 8.89 centimeters per radian, because if I took this radius again and laid it over here, that would sweep out 1 radian. And that's going to make radians cancel, which is what I want. So 4.71 times 8.89 gives me 41.9 centimeters per second. Cool. Okay, we'll come back to these other examples in the next video. Thanks for listening.